Welcome to Pavendars, webinars for the pavement community. My name is Andrew Braham, and today we're going to talk about comparing layer types for the use of PavementME for asphalt emulsion full depth reclamation design. This work is based on Dr. Sadie Casillas' master's thesis research with the same title. Dr. Casillas obtained her Bachelor's of Science in Civil Engineering in 2013 from the University of Arkansas with honors, and she obtained both her master's and her doctorate also in civil engineering from the University of Arkansas. Her LinkedIn profile is posted here and also down in the comment section below. In order to talk about her research, which looked at FDR in PavementME, let's start with a little bit of background of FDR. Full depth reclamation, or FDR, is asphalt concrete plus base course plus potentially sub-base course, all treated, pulverized, mixed, and compacted together. FDR can be treated with asphalt emulsion, asphalt foam, or Portland cement, and what happens is this pulverized or reclaimed asphalt concrete base and subgrade is all mixed together into a single, thick, 6 to 16 inch stabilized layer. And the nice thing is the stabilized layer can increase capacity, and it has a 30 to 50% cost savings over a traditional remove and replace, and a 50% reduction in greenhouse gas emissions. And so any sort of existing distresses that are in your asphalt concrete pavement are all removed, and you create a new stabilized layer. So it's important to note that both bound and unbound material is reclaimed together, stabilized, and placed as a new semi-stabilized layer. So that's a little background on FDR. When we think about PavementME, when you're reading literature and looking at resources, you'll also hear PavementME referred to as MEPDG or AASHTO. There are many different names out there based on when the document was written, but the key is the concept of mechanistic empirical, and that is the ME in PavementME and MEPDG. And in short, PavementME, or mechanistic empirical design, recognizes that loads or stresses are applied to a pavement and deflections or strains result. This is kind of the key of the mechanistic portion. The empirical portion is the incorporation of both traffic and the environment. So this combination of the mechanistic and the empirical portions are what makes PavementME. And if you're interested in learning more, there's actually a separate Pavenar from December 13th, 2020, and it's titled, What is Mechanistic Empirical? And you can find out a whole lot of information about PavementME in that Pavenar. So what Sadie did is Sadie explored this intersection of FDR, or full depth reclamation, and PavementME. When you take a step back and you look at the inputs into PavementME, there's two types of inputs that you can place. You can either say the material is a fully bound material, which is asphalt concrete, or it is an unbound granular material, or an aggregate base. So when you're looking at inputting material properties into PavementME, you're either saying the material is fully bound or it is unbound. Now the challenge with FDR is that FDR is semi-bound. It does not behave as a fully bound material, and you can see here that you could potentially say that you have a A26 soil as your subgrade, then 8 inches of FDR, and you could say that FDR is asphalt concrete. And then there's a surface course on top of the FDR and 1 inch of asphalt concrete. But one way to represent FDR in PavementME is by saying it's an asphalt concrete material. But the other way of representing FDR in PavementME is saying it is unbound material. So again, the exact same pavement structure, the exact same materials, but instead of calling the FDR 8 inches of asphalt concrete, you could say that FDR is 8 inches of unbound granular material. However, FDR isn't asphalt concrete and FDR isn't unbound granular material. So if you're doing a pavement design with PavementME and FDR is one of your layer materials, it doesn't really have a home in PavementME currently. However, PavementME does have distinct tests that need to be run for asphalt concrete and for aggregate. So PavementME has distinct tests that need to be run for fully bound materials or fully unbound granular materials as inputs. And so what Sadie did is she took a look at the exact same material, full depth reclamation, but she ran tests for asphalt concrete on the FDR materials, and she took that same material and she ran tests for unbound granular material. So for asphalt concrete, when she used the 1 inch of asphalt concrete as a surface, or 25 millimeters, and the 200 millimeters of FDR as asphalt concrete, or the 8 inches, she took that asphalt concrete and ran all the asphalt mixture tests. She ran the uniaxial dynamic modulus, she ran the IDT dynamic modulus, the creep compliance, and the IDT strength. So all of the required tests for asphalt mixtures. And then she also took the asphalt emulsion residue and ran the complex shear modulus and the phase angle. So she took all of the tests that should be run for asphalt concrete and ran them on the FDR material. And then of course we have our A-2-6 subgrade soil underneath. Now she also took the exact same FDR material but treated it as an unbound granular material. So in addition to running the asphalt concrete tests, Sadie went ahead and ran the test that's required for unbound granular material, which is resilient modulus. And so she got a set of data of FDR's property as a bound material, as asphalt concrete, and then she got a second set of data as FDR as an unbound granular material using the resilient modulus test. And so what she did then is she put this information into PavementME. So both sets of simulations had a surface course, just 25 millimeters of an asphalt concrete surface course. Then she took 200 millimeters or 8 inches of FDR and she represented FDR as asphalt concrete or AC or a fully bound material. And she took FDR as an unbound granular material or a UGM or an aggregate base. And then we had the A-2-6 subgrade soil under there. Now she also looked at 3 ratios of bound and unbound material. So if you recall, the definition of FDR is taking unbound material, bound material, and reclaiming those together. So she took 3 ratios. So one ratio was 75% wrap and 25% subgrade. So 75% bound material, 25% unbound material. And then also decreasing amounts of bounded wrap to a 50-50 split. So in a sense, if we have 200 millimeters of FDR, that's 8 inches, that means she looked at a pavement structure where 150 millimeters was asphalt concrete and 50 millimeters was unbound and subgrade material. That's the 75-25. She went to 62.5% bound and then down to 50-50, where of that FDR, 100 millimeters was asphalt concrete and 100 millimeters was unbound or subgrade material. And so this allowed us to look at the impact of having a different percentage of bound material versus the unbound material in the FDR structure. She did full mix designs for those 3 ratios of bound and unbound materials, and the mix designs had anywhere from 11 to 13% air voids. About 2.5 to 3.5% water was added in order to get the coating that we needed for the asphalt emulsion, and then 4.8% to 6% asphalt emulsion content. So this is a really nice little study because we looked at different amounts of wrap and unbound material, and then we did the mix design. So we were also kind of looking at these influences of the different materials as well. So what were some of the results that she found? Well, she ran all of the tests for asphalt concrete and for unbound granular materials, and then she put them into PavementME. So let's take a look at one of the tests that goes into the bound materials, the asphalt concrete. And that's the dynamic modulus. And so you can see here, she had the three different types of FDR material, the 50/50, the 62% wrap, and the 75% wrap. And you can see that higher percentages of wrap equaled a lower modulus. You can also see that as temperature increases, the loads slow and the mixes converge. So when you're looking at a dynamic modulus curves, the mixes on the right, or the data on the right side of this curve, that tends to represent either lower temperatures or faster loads, and the reduced frequencies on the left, where they start converging, indicates either higher temperatures or slower moving loads. And you can see how they fan out as you get the lower temperatures and faster moving loads. And as you get the higher temperatures and the slower moving loads, they start converging on the left-hand side. Also note that the geometry impacts the modulus. So we mentioned that we ran two different geometries. One was a uniaxial configuration for dynamic modulus, and the other one is the indirect tensile strength configuration for dynamic modulus. And you can see here that the uniaxial modulus created higher modulus values. The uniaxial configuration created higher modulus values versus the IDT configuration. There were similar trends to what we see here with the IDT strength at minus 10 degrees Celsius for the asphalt concrete. And then when you looked at the unbound granular material, it was actually a parabolic relationship where the 75% wrap had the highest resilient modulus when we were looking at the unbound granular material. So this just kind of gives you an idea of how when you're just running the tests in the lab, you don't really see the same trends when you're treating FDR as a fully bound asphalt concrete material versus an unbound granular material or a aggregate base type material. And that's pretty important because then as we move into the simulations, you can see that there are some differences. So on the x-axis, we have FDR as an asphalt concrete material. And on the y-axis, we have FDR as an unbound granular material. And this is how much rutting there is in the asphalt concrete layer. And you can see that the 50% and the 62% wrap had similar rutting values as for unbound granular material and asphalt concrete. But when you got to those higher levels of wrap, we actually saw that PavementME predicted higher rutting if you put in FDR as an unbound granular material. And I can't stress this enough. Remember, this is the same material that we're testing. We're just using different tests to characterize it. And then we're using those tests to call FDR either an unbound granular material or asphalt concrete. But in fact, these are the exact same materials. We're just calling them something different in PavementME, and we're using different tests in order to characterize the material as an input into PavementME. So this is just the asphalt concrete rutting. But what about the total rutting in the entire pavement layer? And this is important because this will include the FDR layer itself. And you can see here, it's even a more extreme scenario. All four of the mixes produce higher rutting if you categorize FDR as an unbound granular material. And what this means is that those lower percentages wrap, the 50% and 62.5% wrap, have the majority of rutting occurring in the FDR layer and subgrade material. It's also important here to note that PavementME has minimum required values or maximum required values. You can't have more than 19 millimeters of total rutting, and both the 75% and the 62.5% wrap failed as an unbound granular material. So those FDR layers that had higher percentages of wrap actually failed as an unbound granular material, but they did not fail as an asphalt concrete material. So here we have, again, the exact same mix. It's actually failing when you categorize FDR as an unbound granular material, but it does not fail if you take the exact same material and you run the test and categorize it as a bound layer or an asphalt concrete layer. So this is a very interesting finding. We also looked at bottom-up fatigue cracking, and this is the only output where the asphalt concrete representing FDR as an asphalt concrete layer, you got worse results than as an unbound granular material. And this is a little unexpected because FDR should provide some tensile resistance, but when you're looking at unbound granular material is not supposed to have any tensile resistance. So in a way, PavementME is kind of setting up FDR to fail as an asphalt concrete layer with fatigue cracking, because if you categorize it as an unbound granular material, PavementME itself cannot have a crack forming in an unbound material. Cracks can only occur in asphalt concrete. So the bottom-up fatigue cracking, this is the only one where FDR performed worse as an asphalt concrete layer, but it's also the only one where literally it could not fail as an unbound granular material. So that's bottom-up fatigue cracking, kind of the traditional fatigue cracking. What about top-down cracking? Here, the cracks did not initiate in FDR or as asphalt concrete or as an unbound granular material. That's because these cracks are initiating in the asphalt concrete surface layer. But when this happened, FDR tended to perform better than an unbound granular material. So the FDR as an asphalt concrete tended to perform better than FDR as an unbound granular material. So here, when you're looking at top-down cracking, where the crack initiates in that 1-inch surface layer of asphalt concrete, again, FDR represented as asphalt concrete tended to perform better. Now we also got thermal cracking outputs, but thermal cracking was the same for all 8 combinations. It was 3.45 meters per kilometer for all 8 of the combinations. So we saw no difference in thermal cracking whether FDR was an unbound granular material or asphalt concrete, and there was no difference between the geometric conditions or the geometric configurations of the dynamic modulus or the different percentages of RAP in the mixture. The final output is International Roughness Index. So we have, again, our 4 mixtures along the left there. I simply rounded the IRI prediction to the nearest 5 millimeters per kilometer just to kind of make the numbers a little easier to look at. But you can see here, regardless of the mix, the IRI is around 2,000 for all 4 mixtures. And it's a little higher as FDR is an unbound granular material. But the largest difference was 23%, and this was the smallest difference between the 2 materials of all the outputs, is this 23%. Now, I didn't get into this much, it's described much more in the paper, but there's also different traffic levels depending on the ratio of RAP to subgrade material. And we found that for unbound granular materials, the traffic levels did not impact the IRI as much as the asphalt concrete. And again, this is the most similar of all distresses between asphalt concrete and unbound granular material, the final International Roughness Index. So in conclusion, we did find that dynamic modulus showed the ability to differentiate the mixtures. We found that 75% RAP as an unbound granular material provided the highest level of distress. And in general, for all distresses but bottom-up fatigue, FDR as an asphalt concrete layer provided the lowest distress values. Now, some things that did come up is that, especially with dynamic modulus and PavementME, we need to confirm if the viscoelastic range is the same for FDR as asphalt concrete. So the linear viscoelastic range for asphalt concrete is pretty well established, and we were just assuming that it was the same range for FDR. So that's something that needs to be dug into a little more. And also the IDT configuration was developed and used because when you take cores out of the field, you punch a 6-inch hole into the road with the core barrel. So it's very easy then to run that IDT configuration in the lab, especially on the thinner pavement layers. But we need to ask the question, is this an appropriate configuration for semi-bound material? Because it is a lot harder to run tests with those smaller samples and cut nice flat faces on to put the gauge points on for semi-bound materials versus fully bound materials like asphalt concrete. So just logistically, it's a little harder to make samples out of FDR for the IDT configuration of dynamic modulus. So in my mind, there were actually a couple more questions generated than answers from this study. I think that it was showed that there is a difference when you take the exact same material, but you classify it in two different ways in PavementME. So I think you do need to take care when you choose how to classify FDR and PavementME. I think this could be expanded also into CIR or cold in place recycling, and perhaps HIR and hot in place recycling. And I think this just shows, though, the challenges with taking these semi-bound materials and asking, well, how do they behave? They don't behave like an unbound material, and they don't behave like a fully bound material either. And so I think there's a lot of work that could be done in better understanding and better classifying this material in PavementME. So if you're interested in learning more, I just scratched the surface on some of the topics, but here's a citation for the full paper, and I'll put the DOI link down in the comment box. And so thank you very much for joining me. I appreciate you taking the time, and I hope you have a great day.